So Dr. Devin McAuley is a professor at Michigan State in the Department of Psychology, and he is the director of the Cognitive Science program there and a member of the Neuroscience program. Did his undergrad and grad school at IU, Indiana University, receiving a BA in math and computer science and doing a master's in computer science as well, and then did joint PhD in computer science and cognitive science. Then went on to complete postdoc studies in psychology at Queensland and Ohio State University, where he was in music cognition. Dr. McAuley's research interests include auditory perception, attention, memory, music cognition, cross-modal processing, and temporal control of behavior. The topic of this talk is rhythm and developmental stuttering.
Good morning, everyone. Thank you for the opportunity today to talk about some of our work on rhythm and developmental stuttering. I wanted to start out by first acknowledging my colleagues on this project. The work I'm going to share is very much a collaborative effort with Dr. Chang, who directs the University of Michigan Speech Neurophysiology Lab, Dr. Emily Garnett, who is also at UM in the Speech Neurophysiology Lab, Dr. Homing Chow at the University of Delaware, Dr. Liz Wieland, who completed her graduate work at Michigan State University. I also wanted to acknowledge our funding sources for this work. This work has been supported by both the National Institutes of Health and the Grammy Foundation. Today's talk is in 4 parts. First, I'm going to provide a little background on developmental stuttering. Then I'm going to motivate an internal beat deficit hypothesis for developmental stuttering. Next, I'm going to share some of our work on rhythm perception in children and adults who stutter as tests of the internal beat deficit hypothesis. Finally, I'd like to discuss some caveats for assessing rhythm and development in general. Stuttering is a speech disorder characterized by repetitions, prolongations of sounds, and frequent hesitations and pauses, which disrupt the rhythmic flow of speech. Chronic stuttering affects a significant portion of the population, approximately 3 million individuals in the US. Children who develop chronic stuttering face lifelong struggles that can impact academic achievement and lead to a range of negative psychosocial consequences. Stuttering onset in children is typically between 3 and 5 years when children are first putting together words into a sentence. Up to 70 to 80% experience full recovery, however, yet neural mechanisms of developmental stuttering, including reasons that some children recover, are poorly understood. One striking finding is that stuttering can be markedly alleviated even in the most severe cases when individuals are synchronizing speech with a metronome, speaking in unison with another, or in the context of singing. One possibility is that metronomes, choral speech, and singing may induce fluency in people who stutter due to the fact that these methods provide an external pacing signal. This suggests that individuals who stutter may have a deficit in internal timing of their speech. Considered in the context of rhythm perception, we propose that individuals who stutter may have a deficit in the internal generation of a periodic beat. I'm going to refer to this in this talk as an internal beat deficit hypothesis. Motivation for an internal beat deficit hypothesis comes from a number of sources. I'm going to focus here on one. In a fMRI study by Chang and Zhu, the authors showed that children who stutter have reduced resting state functional connectivity in a network of subcortical cortical brain regions previously implicated in beat perception. These include the putamen, SMA, and premotor areas. This is of particular interest because these brain areas are part of a basal ganglia thalamic cortical network that has been previously implicated in beat perception by a number of researchers. Next, I'm going to turn to our work on rhythm perception in children and adults who stutter. This work tests the internal beat deficit hypothesis that I just described. First, some general methods that will apply to both of the children and adult studies. First, the task. The task we used was a rhythm discrimination task, which for the children was framed in the following way. So children were told that they would hear Randy the drummer play a rhythm on his drum 2 times. Then either Sandy Same would play the same rhythm back, or Doggy Different would play a different rhythm. Their job was to tell us whether the last rhythm that was played was by Sandy Same or Doggy Different. So thereby making a same different rhythm discrimination judgment. There were 2 types of rhythms, simple rhythms and complex rhythms. Here is a notated example of each type. Rhythms consisted of a sequence of time intervals. In this diagram, the dark vertical lines correspond to tone onsets, and dashed vertical lines correspond to implied beats based on the temporal structure of the rhythm. The sequence of intervals is notated as a series of integers here, which indicate the relative durations of each intertone onset interval in the sequence. The base time interval is notated by a 1, and note that all other intervals are multiples of the base time interval. The key difference is that simple rhythms always have tones on beats, reinforcing the beat, while complex rhythms do not. Each simple rhythm had a complex rhythm pair that consisted of the same set of time intervals, but in a different order, thereby controlling for the specific intervals that listeners heard when making comparisons between simple rhythms and complex rhythms. To assess performance on the rhythm discrimination task, we use signal detection measures D prime and C, D prime corresponding to a measure of perceptual sensitivity, and the response criterion measure C, allowing us to assess any response bias individuals have to say same or different. There are 2 main predictions. One is a general prediction about simple and complex rhythms. So there have been a number of studies that have shown that simple rhythms with an explicitly marked beat are better discriminated than complex rhythms with a weakly or inconsistently marked beat. This goes back to work by Pavel and Essens, also work by Gran and Brett in 2007. Second prediction is that individuals who stutter will show poorer rhythm discrimination than controls, especially for complex rhythms, which require internally generating a beat. Let's now turn to our work with children who stutter using this paradigm. So in the work with children, there were 17 typically developing children, 17 children who stutter. They were ages 6 to 11 years. All were monolingual native speakers of English with normal hearing. And all were given a speech language and cognitive battery. The task that children performed was the same different rhythm discrimination of simple and complex rhythms as I just described. In total, there were 7 simple rhythms and 7 complex rhythms, each presented in same and different forms for a total of 28 trials. The base inter-onset interval rove between trials, so the tempo that they heard on a given trial varied randomly from trial to trial, and it varied between a base inter-onset interval of 165 milliseconds to 205 milliseconds. And as I just described on the preceding slide, signal detection measures D prime and C were used to assess performance. Okay, so let's look at the results. Here on the left pair of bars, you see performance for typically developing children, and on the right pair of bars, you see performance for children who stutter. On the y-axis, you have performance measured as D prime. And what you can see are 2 patterns. The first pattern is that overall, simple rhythms were better discriminated than complex rhythms. So you can see that by comparing the dark bars to the unshaded bars. Second, children who stutter performed worse than typically developing children, especially for complex rhythms, in line with the internal beat deficit hypothesis. Here is a graph showing response criterion or response bias. There were no differences between the 2 groups, and there were no differences between simple and complex rhythms. Overall, there was a slight tendency for children to respond same. And this is a bias that has been seen in a number of different studies. Next, in an fMRI study, we were able to look at resting state functional connectivity in these same children. Here, all of the children completed an MRI to gather anatomical data and a resting state functional scan that examined intrinsic connectivity or correlated activity between regions in the BGTC network of regions previously implicated in beat perception. What you can see in this graph comparing columns A and B is that age-matched controls showed in column A showed greater intrinsic connectivity in the rhythm network compared to children who stutter, shown in column B, replicating the earlier work by Chang and Zhu. The subtraction is shown in column C. This next set of graphs shows the relationship between resting state functional connectivity and rhythm discrimination performance for children who stutter, red lines, and controls, green lines. What you can see in these scatter plots is that greater functional connectivity was associated with better rhythm discrimination for age-matched controls, but not for children who stutter. So there was a positive correlation between rhythm discrimination score, standardized measure of rhythm discrimination score, and correlated activity in the BGTC network for control participants, but not for children who stutter. Okay, next, I'm going to turn to some of our current work on rhythm of perception in adults who stutter. Adults who stutter are chronic stutterers who are a very heterogeneous population. They vary in stuttering severity and have potentially developed a wide range of compensatory strategies, which makes them different from the work with children. Okay, here are some of the methods. So for the study that I'm going to talk about, there were 18 adults who stutter, 18 age-matched controls, same distribution of male and female participants. Participants range from age 18 to 53 years of age. All were monolingual native speakers of English with normal hearing. All were given a speech, language, and cognitive battery. In this study, there were 12 simple rhythms and 12 complex rhythms, both presented in same and different formats. So the task was the same different rhythm discrimination of the simple and complex rhythms. And we use signal detection measures D prime and C to assess performance. Here are the results. Okay, on the left, pair of bars, we can see simple rhythm discrimination. And the right pair of bars, we see complex rhythm discrimination. And the more darkly shaded bars are the adults who stutter, and the more lightly shaded bars are the control participants, or the age-matched control. On the y-axis, you have sensitivity or rhythm discrimination performance as measured by D prime. And again, you can see two things in this graph. You can see that simple rhythms are better discriminated than complex rhythms as predicted. You also see a decreased performance specific to complex rhythms for the adults who stutter compared to the age-matched control. We did not see a group difference for the simple rhythms. So in line with the internal beat deficit hypothesis, we saw poor rhythm discrimination for complex rhythms in adults who stutter compared to age-matched controls. Here's a graph showing response bias. Similar to the work with children, we see no difference in response bias or the response criterion for simple or complex rhythms, and no difference between adults who stutter compared to control participants. Overall, there was a slight tendency to respond similar to the work with children. As you may notice in this graph, in these bar and whisker plots, you will see a wide range of performance for both the control subjects and the subjects, adults who stutter. To explore this in more detail, we looked at individual differences in the AWS group. This graph shows the relationship between operation span, our measure of working memory capacity, and rhythm discrimination, combining simple and complex rhythms. As you can see, greater scores on the operation span measure were associated with better rhythm discrimination. The same pattern was observed for both simple and complex rhythms. Next, we looked at individual differences in stuttering severity within the AWS group. This graph shows the relationship between stuttering severity and simple rhythm discrimination after controlling for differences in working memory capacity that we observed. Stuttering severity is on the x-axis and simple rhythm discrimination performance is on the y-axis. Notably, when we partial out the contribution of working memory capacity to rhythm discrimination performance, we find a robust negative correlation between stuttering severity as measured by the stuttering severity index and simple rhythm discrimination. So increased stuttering severity was associated with poorer rhythm discrimination. This graph shows the same relationship for complex rhythm discrimination. On the x-axis is stuttering severity, and on the y-axis, complex rhythm discrimination. You can see the same negative relationship. Greater stuttering severity is associated with worse rhythm discrimination. Let me sum up the results from our experimental work. In general, the results I presented in this talk provide support for the internal beat deficit hypothesis proposed for developmental stuttering. Children who stutter show worse rhythm discrimination than age-matched controls, especially for complex rhythms. Resting state functional connectivity in the BGTC network is stronger and better predicts rhythm discrimination for age-matched controls compared to children who stutter. Adults who stutter similarly show worse rhythm discrimination than age-matched controls, especially for complex rhythms. Finally, for AWS, greater stuttering severity is associated with worse rhythm discrimination for both simple and complex rhythms after controlling for working memory capacity. Finally, I'd like to finish this talk by discussing some caveats for assessing rhythm and development in general. First, rhythm is not a unidimensional construct. I think that's something that's very important to keep in mind. When we talk about rhythm perception includes perception of beat, perception of meter, perception of grouping. Rhythm discrimination is often assumed to involve comparing the sequence of time intervals to make a same different discrimination judgment. But I think it's important to keep in mind that same different judgments about rhythms could also be based on perceived grouping. It's very possible that when a rhythm is altered, where like, let's say a pair of adjacent intervals are swapped to make a different rhythm, that change could also influence perceived grouping. And so as a result, participants potentially may be able to make same different judgments accurately by just comparing the grouping of the elements. Okay, so this I think is something very important to keep in mind in studies that look at rhythm discrimination and want to make inferences about timing processes with either in one group or comparing comparing typical and atypical development. Next is an issue that is related to the single cause fallacy. So there has been extensive debate in the field evaluating, contrasting different models of timing. Specifically, there has been work comparing interval versus beat-based or entrainment mechanisms of timing. And behavioral and neural evidence has been reported that supports both types of mechanism, with the BGTC network linked to beat-based timing and the cerebellum linked to interval-based timing. If individuals who stutter have impaired beat-based timing, it's possible that they can compensate by engaging interval-based timing mechanisms. So it's possible for some of the timing assessments that have been developed to examine different neurodevelopmental disorders, that those timing assessments may show no difference, in part due to compensatory strategies involving the engagement of interval rather than beat-based timing mechanisms. Finally, I think it's important to note that children and adults differ in their preferred tempo. So there have been a number of studies that have shown developmental profiles prefer tempo, and it's important to consider that rhythm perception may differ as a function of tempo, and moreover may be best for children with typical and atypical development at different tempi. So children in general have a faster preferred tempo than adults do. And there may very well be differences in preferred tempo in different developmental disorders. In the work I presented examining rhythm discrimination in children in age-matched controls, we had to speed up the tempo of the rhythms from previous adult studies using the same rhythms in order for children to be able to reliably do the task. And so, depending on the tempo that is picked, one might, the caveat is that one might reach different conclusions based on solely the tempo that is selected for the particular task. Okay, I think I will stop there. I wanted to thank you for your attention, and I look forward to your questions in the discussion period.